Lesson 8.4, intersections of lines in 2-space and in 3-space. We're pretty familiar with how lines can interact with each other in 2-space. They can intersect, or they can coincide, or they can be parallel to each other. If they intersect, there is one solution to the system of linear equations. If they coincide, there's an infinite number of solutions, and if they are parallel, then there are no solutions whatsoever. In this lesson, we're going to basically do the same thing as we've done before, substitution and elimination, with our lines in 2-space, and then we're going to transition into dealing with lines in 3-dimensional space. So example 1, we can right away get into example 1. It says that we need to classify each system as having 0, 1, or infinitely many solutions. I'm going to write down example 1a, but I'm not actually going to do it. Line 1 is 4x minus 6y equals negative 10. Line 2 is 6x minus 9y equals negative 15. So what we would do here is we would multiply our equations, both equations, by a different factor in order to get the same coefficient in front of either the x or the y. And once we do that, we can use substitution or elimination to, well, that would be using elimination. You'd use elimination in that case to eliminate one of the variables, solve for the other variable. Once you have a solution like y equals whatever it is, you sub that back into the other equation, or one of the equations, in order to find out what x is, and there's your solution to the linear system. Now, if you're working in a problem like this and you see that equation 1 and equation 2 are actually multiples of each other, which is what we have in this case, if I multiplied each term in equation 1 by 3/2 or 1.5, I would get equation 2. So these are actually equivalent equations. So if you're in a situation where you have equivalent equations, even though they might not look it, these ones are pretty easy to determine, but sometimes it doesn't look equivalent at all, then you know that they're the same line actually, and that they, whatever they look like, they coincide. They're right on top of each other, and then there are infinitely many solutions. So that's something to watch out for as well. One thing that we do want to talk about briefly, because it's going to help us immensely when we move from 2-space to 3-space, is something about these lines. So the two lines in example A they actually coincide. So they're right on top of each other. But they are going to then share a property. Something is going to be true about both of these lines. And what's true about them is that their normal vectors, whatever they are going to be scalar multiples of each other. The normal vectors are heading the same direction. They are parallel to each other. So that little trick, so whether the first two lines coincide or whether those lines are parallel, if they're parallel or if they coincide, then every single normal vector of line 1 is going to be parallel to every single normal vector of line 2. So what we can do is we can actually find our normal vectors using an earlier strategy that we have used. The normal vector for line 1 is the vector 4, -6, and the normal vector for line 2 is the vector 6, -9. And so we can see that since n1 is equal to 2/3 of n2, that would mean that the normal vectors are parallel. Therefore, the original lines are either parallel or coincident. Okay? Now we can go ahead and check whether or not they're parallel or coincident by looking up here, and we notice that, yes, indeed, if I multiply all of L2 by 2/3, I will end up with the line L1. So if these guys, if they don't match up by that factor, then the lines will be parallel. But if they do, then they would be coincident, which means they intersect at an infinite number of points. In example 1b, example 1b, we're going to do this one. We are given the lines in vector form. Line 1 is xy is equal to 1, 5, that's our position vector, plus some scalar multiple of our direction vector, negative 6, 8. And we have a second line, x comma y is 2, 1, that's our position vector, times some scalar multiple of our direction vector, 9, negative 12. And again, there are a couple different ways to do it and a couple different ways to think about it. We're going to do this algebraically. So I'm going to call this equation 1 and this equation 2. And we're going to write these equations in parametric form. So writing these equations, each of them in parametric form, I've got equation 1. It's got x equals 1 minus s. Y equals 5 plus 8s. And over here in equation 2, we have 2 plus 9t and 1 minus 12t. For line 1, we have x equals 1 minus 6s. Y equals 5 plus 8s. Over here for line 2, we have x equals 2 plus 9t and y equals 1 minus 12t. Now we remember that when two lines intersect, there is an ordered pair, xy, that will satisfy both equations. Okay? So that means that this x and this x will be equal when this y and this y are equal. If that's true, they will intersect. If that's not true, they won't intersect. Okay? So that's what we're looking at here. Well, now I've broken it up into its parametric equations, and I've just explained that if we can get this x to equal that x and this y to equal that y, then we have found a solution. So that's what I'm going to do. I'm going to equate the x and y variables. So when I equate the x's, we get 1 minus 6s, equals 2 plus 9t. And we have, do my second equation over here, the y's. If I equate the y's, I get 5 plus 8s equals 1 minus 12t. Okay, now I've created two new equations by equating these, okay? Let's simplify. I'm going to put all my variables on the right side of each equation and have the value, just the constant on the left side. So here I'm going to subtract 2 from both sides and add 6s to both sides. I'm going to call that now equation 3. Here we're going to subtract 1 from both sides and subtract 8s from both sides. Call that equation 4. So now you can see what's happened. Now I have two equations again and two variables. And if we look at our variables s and t, the s's come from line 1. This s comes from right here. Okay, what does that mean? Well, that means that this s is the same as this s, which means that this s is the same as this s. Okay, that also means that since t comes from here, and it got copied into this parametric set of equations, that this t is going to equal this t. So if we can find the solutions for this system of equations, where this s equals this s at the same time as this t equals this t, because that's true up here, then we can say that they do intersect. Okay? Here we go. We're going to put them on top of each other, and we're going to use substitution or elimination. In this case, it looks like I'm going to use elimination because I don't have any of these variables with a coefficient of 1. So I'm going to make these equal each other. I'm seeing that my t coefficient is 9 here and 12 there. So I'm going to take equation 3 and multiply it by 4. Then I'm going to take equation 4, multiply it by 3. That's going to give me a numeric value of 36 in front of each of my t's. So multiplying by 4, we get negative 12 is equal to 24s plus 36t. Multiplying equation 4 by 3 gives me 12 equals negative 24s, minus 36t. And actually, I'm seeing an error. So I subtracted 2 from both sides here, but I ended up at negative 3. That should be negative 1. 1 minus 2 is negative 1. And then when I multiplied equation 3 by 4, I should have ended up with negative 4 here. Okay, so we're not quite done. We can keep going. They're not equivalent equations. And we can keep going. So I'm going to add these together. And that eliminates my t's. I've got negative 4 plus 12 is 8. But now I also have 24 plus negative 24. Well, that is 0 s's. So is there any value of s that can make this statement true? No, because anything times 0 is 0. It will never be equal to 8. So this equation is not true for any value of s. No value of s will make this true. Therefore, no solutions to this system. Okay, and if there are no solutions for this system, for an s and t, then there are no solutions for this system. There's no value of s or t that can get these lines to go through the exact same point. Now let's backtrack, because we should have been able to come to that a lot more quickly. If we take a look at the direction vectors for each of our lines, then you can see that the direction vectors are actually multiples of each other. That you could multiply the vector direction in the direction vector in equation 1 by negative 3/2, and you would get the vector direction vector for equation 2. Since they are scalar multiples one of another, then they're parallel. It doesn't matter where you start. These lines, line 1 and line 2, are going to be parallel to one another, and therefore there are no solutions to the system. I'm going to write that down. Alternate method. Since direction vector 1 is negative 2/3 of direction vector 2, these lines are parallel. Well, they're not they don't intersect, I should say. These lines do not intersect. Now we don't know at this point whether or not they are parallel or coincident, but we can go ahead and look at them, and if they were coincident, then the position, the point 1,5, would lie on line 2 as well as line 1. And equally so, the point 2,1 would lie on line 2 as well as line 1. Okay, so we can just check to see if 1,5 can satisfy the second set of parametric equations. Okay, so that's what we can check. We can check to see if 1,5 satisfies or lies on. Check to see if 1,5 lies on line 2. In order to do that, we just take our parametric equation. We sub in 1 for x, 5 for y. 1 for x, 1 equals 2 plus 9t. And 5 equals 1 minus 12t. And then we can solve and see if we can get see if t is equal to the same thing. Sorry, rewriting it over here. 5 equals 1 minus 12t. So solve for t over here. Subtract 2 from both sides. Divide by 9. T equals 1 over 9, negative 1 over 9. Let's see what it equals over here. We're going to subtract 1 from both sides. Divide by 12. T equals 1/3. Negative 1/3. So because the t values are different, the 0.15 is not on line 2, which tells us that they are parallel rather than coincident. Therefore, 1 and 2 are parallel. And there are 0 solutions to the system. Okay, as we move to looking at two lines and how they relate to each other in 3 space, there are our regular options. So for instance, on a 2-dimensional plane, lines can intersect. Well, that's the same in 3 space. If those 2 lines find themselves on the same plane and they're not parallel, then they'll intersect. Okay. They may also be parallel on the same plane, in which case they would not intersect. That would be no intersections. They're parallel, having the same slope. But one difference in 3-dimensional space is that even if lines intersect, they can be lifted one from another onto a different plane. And so these two, I can't really show it that great in the video, but you can see, okay, so these now will never cross. Okay, these lines are called skew. And even if I were to tip my purple one or rotate it around, I could rotate it around this brown marker and they would still never touch. What if I rotated it about its middle? Then eventually I'd come to a place where I would cross the plane that the brown marker is on and then they would intersect. But otherwise they're not going to intersect at all. So those are called skew, and that's the 4th option that's different. So you have intersecting on the same plane, you have coincident lines with an infinite number of solutions, you have parallel lines on the same plane, and then you have they do not intersect, no solutions, and then you have lines that are skew, that even though they're not parallel, they're on different planes and they never intersect. Okay? So just quickly the notes there. Linear systems in 3 space. There's 4 options. 1, they can be distinct and intersect. They can be coincident, same line, infinite solutions. They can be distinct, so 2 different lines, and parallel, in which case they will not intersect. And they can be distinct, well, let's just write skew. They can be skew, which is distinct and not parallel. All right, there's your 4 options for the way that lines relate to each other in 3 space. And we can use a lot of math tools that are common to us already in order to determine if a linear system satisfies any of these 4 situations. And they will be one of them. That's what we do in the next handful of examples. In example 2, we are going to determine if these 2 lines intersect in 3 space, and if they do, we're going to find that point of intersection. X, Y, Z, line 1 is X, Y, Z equals 5, 11, 2, plus some scalar multiple of 1, 5, negative 2. Line 2 is X, Y, Z equals 1, negative 9, 9. plus t times 1, 5, negative 2. All right, well, right away, what do you see? The two direction vectors, the direction vector for line 1 and line 2 are the same. So we know for sure that line 1 and line 2 are parallel. They're already parallel. We just need to know if they're distinct and parallel, then they will have no intersection. If they are coincident, then they have an infinite number of solutions. So if the lines are coincident, then the coordinates from line 1 will lie on line 2. Okay, so the x from line 1 will will be equal to 1 plus t times 1, at the same time as 11 will be equal to negative 9 plus t times 5, and 2 will be equal to 9 plus t times negative 2. So I'm going to set up the parametric equations for line 2. So I've got line 2. Parametric equations are x equals 1 plus t, y equals negative 9 plus 5t, and z equals 9 minus 2t. And now I just need to substitute the coordinates. Sub 5, 11, 2, sub 5, 11, 2 into L2 and solve for t. And solve for t. Now, if I get the same t for all of them, then I know that this point satisfies the equation here as well. If I get a different value of t, then I know that 5, 11, 2 is not on line 2 and that they are distinct parallel lines. So here we go. We've got 5 equals, this is for x, 5 equals 1 plus t. 11 for y equals negative 9 plus 5t. And for z, 2 equals 9 minus 2t. All right, here we subtract 1 from both sides. We get t equals 4. Here we're going to add 9 to both sides. Divide both sides by 5. T equals 4. Here we're going to subtract 9 from both sides. I'm going to get negative 7 equals negative 2t. Divided by negative 2, we get t equals 3.5, or 7 over 2. Okay, since these t values are not all identical, then the point 5, 11, 2, does not lie on the line. And these lines are parallel and distinct. Therefore, L1 is parallel to L2, and they are distinct. So not coincident. There is a second way of doing this problem, very similar to what we did in the previous example, and it requires getting an equation, the parametric equations for L2 and L1. So we'll just do it for L1 for a sec. 5 plus s, y is 11 plus 5s, z is 2 minus 2s. And now what we see is we have an equation for x and x, y and y, z and z. So if these lines were to intersect, there would exist an x, y, z that satisfies all of these and all of these. Okay? So what you would end up doing is you'd have an equation where you set the x's equal to each other. 1 plus t equals 5 plus s. And you'd reduce that. You'd have an equation that sets the y's equal to one another. Negative 9 plus 5t equals 11 plus 5s, and a third equation with 9 minus 2t equal to 2 minus 2s. And then what you would do is you would use two of the equations, and you'd put the variables all on one side and the value on the other side, and you'd organize the equation 2 the same way, and then you'd use substitution elimination to solve for either t or s. Then you'd use that to find the s that corresponds, And then you would take that s and t and see if it satisfies the third equation as well. Okay, if it does, then you have an intersection point, a point of intersection. If it does not, then they do not intersect. In this case, you would end up finding out that they do not intersect. Okay, don't do that in example 2. I didn't finish that out because it's pretty much the same as what we're going to do in example 3. In example 3, we're told that two lines do intersect. L1 and L2 do intersect. So we've got L1, which is x, y, z equals 7 to negative 6 plus s times 2, 1, negative 3. And we've got L2, x, y, z equals 3, 9, 13 plus t times 1, 5, 5. So the direction vectors are different. They're not multiples of each other, so I know they're not parallel, and these lines are not going to be coincident. They are going to intersect somewhere. So I'm going to write these each in parametric form. L1, x, y, z, x is equal to 7 plus 2s. Y is equal to 2 plus s. And z is equal to negative 6 minus 3s in L2. We've got x equals 3 plus t, y equals 9 plus 5t, z equals 13 plus 5t. All right, now that we have these equations, we have an equation for x in both lines, an equation for y in both lines, an equation for z in both lines, and this x, y, z is at one point in space going to be the exact same as satisfy line 2 as well. So I'm going to equate my coordinates. My x coordinates over here are going to be 7 plus 2s equals 3 plus t. Y coordinates 2 plus s equals 9 plus 5t. Z coordinate negative 6 minus 3s equals 13 plus 5t. So now I'm going to go ahead and use equation, well, I'll simplify them first and we'll see if any of them look easier than the other ones to use. So here we've got, we're going to subtract t from both sides. So we've got 2s minus t, and we're going to subtract 7 from both sides. It's going to give us negative 4 on the right. That's going to be equation 1. Then here we have equation 2. It's going to be s minus 5t equals 7. Here we're going to have equation 3. It's going to be negative 3s minus 5t equals 19. So I have 3 equations. I can use substitution or elimination, does not matter which one I use. You might be tempted to use substitution if you can say this is s equals 7 plus 5t and then sub that in somewhere else. Maybe I'll do that because I haven't done that yet. So equation 2 then, to isolate s, is going to be s equals 7 plus 5t. And now I'm going to sub that into, let's say sub that into equation 1. So we've got equation 1 is going to be 2, and then instead of s, I'm going to write 7 plus 5t minus t equals negative 4. Here we have 14 plus 10t minus t equals negative 4. I'm going to group my t's together, so I have 9t. And I'm going to subtract 14 from both sides. That's going to be negative 18. Gives me a t value of negative 2. Now I can sub that back into my second equation here in order to find the value of s. So I've got s equals 7 plus 5 times t, which is now negative 2. That's negative 10 plus 7 is going to be negative 3. Now I take this value of t and this value of s, and I've used equation 1 and 2 already, so I'm going to take them and I'm going to sub them into equation 3. I'm going to check that t equals negative 2 and s equals negative 3 satisfy equation 3. So on the left side for equation 3, I've got negative 3s minus 5t, and on the right side I've got 19. Sub in my values for s and t, I get negative 3 times negative 3 minus 5 times negative 2. Positive 9 plus 10 equals 19 equals right side. Therefore what? So this system has a unique solution, but the values of t and s don't tell us where that solution is. So we've confirmed that there is a t and s that satisfy all of these equations when we equated our x, y, and z's. So we do know that they do intersect, but we haven't figured out where they intersect yet. All we need to do is take either our value for t and sub it into L2, because it has a t in it, or take your value of s and sub it into L1, and you'll get the unique point of intersection. You'll get the unique solution. So here we go. I'm going to take, maybe I can bring it down here so that we can see. I'm going to sub s equals negative 3 into L1. That looks like this. X, y, z is equal to 7 to negative 6 plus s, which is now negative 3, times 2, 1, negative 3. Now I just need to work this out. I'm going to do it in 2 steps so that we can see it all. I've got 7 to negative 6. And here I'm going to end up with adding the vector negative 6, negative 3, positive 9. And that's going to reduce to 7 minus 6 is 1. 2 minus 3 is negative 1. Negative 6 plus 9 is positive 3. Since this is now a position vector, x, y, z, that means that the point, therefore, 1, negative 1, 3, is the unique solution. So this is the point of intersection for this system of linear equations. What did we do? We broke each line into its parametric equations. We set the variables, the coordinates equal to one another, x equals x, y equals z, y, z equals z. So we had 3 equations with 2 variables. Well, we only need 2 equations with 2 variables. So we took equation 2, we isolated s in order to do substitution. We could have just lined up 1 and 2 and done elimination, or 2 and 3, or 3 and 1. Either way, we could have used substitution or elimination to find out what t and s are. Okay? Then we have to go into our third equation and say, all right, do this value of t and this value of s satisfy equation 3 as well? If they do, then we have confirmed that there is a point of intersection between these 2 lines. Okay? Because there is an s and a t combination that can make these lines end up at the same place at the same time. We just didn't figure out yet at that point what that place was. So in order to do that, we took our values of t and s and subbed them in. You could sub in t to equation 2 or s to equation 1. Both of them give you the same answer, and if you're not sure of your work, you can do it in both of them, and they both should come out with the direction, the position vector 1, negative 1, 3, which crosses also these two lines, by the way. Or it should say it doesn't cross these two lines, it touches these two lines, which tells us that the point 1, negative 1, 3 is on both of those lines. It is the point of intersection between line 1 and line 2. In example 4, we're going to determine if two given lines are skew. And again, it's pretty much the same process. We've got x, y, z is equal to 5, negative 4, negative 2, plus s times 1, 2, 3. L2 is x, y, z is equal to 2, 0, 1 plus t times 2, negative 1, negative 1. So first thing we can see is our direction vectors. They are not multiples one of another. So these lines are not parallel. So they're either going to intersect once or they're going to be skew. Okay? We're going to set this up the exact same way. We're going to write the parametric equations and then set variables equal to each other. And if you're getting good at it, you don't even need to set up the parametric equations. You know that from line 1, x equals 5 plus s, and from line 2, x equals 2 plus 2t. Y from line 1 equals negative 4 plus 2s, and y from line 2 equals 0 minus t, negative t. And then the z coordinate of each line, in line 1, it's negative 2 plus 3s, and in line 2, it is 1 minus t. Again, you'd simplify each of these. You've got three equations, 1, 2, 3. You set two. You use two of them to do substitution elimination. You solve for t and s. And then you check it in the third equation. And again, you can choose any two equations to do that first part with, and you check it in the third equation. And then you'll find out that it doesn't work out. Left side does not equal right side. Therefore, since they're not parallel and they don't intersect, they're skew. Okay, I'm just going to write the steps of what to do. Steps of what to do. Use two equations to solve for s and t using substitution or elimination. Then sub the values s and t into third equation, which is just the leftover one. Whichever of the two that you've already used, use the other one. Sub the values of s and t into the third equation. If left side equals right side, then they would intersect. If left side does not equal right side, skew, because we already know that they're not parallel. In this case, they end up not intersecting and they're not parallel, therefore they are skew. Okay? Just gonna write that. The lines in the example are skew. So you'll do this in your practice problems. I'm not going to do it here. If you'd like to check the textbook, you can find that on page 468. Example 5 is an application of all of this. We're finding the distance between two skew lines. Okay, so in two-dimensional space, when we have two lines, finding the shortest distance in between them if they intersect, it's always going to be 0, right? Because they intersect. Now, if two lines are parallel to one another, and you want to find the shortest distance between those two lines, are you going to take this line, or this line? Okay, you're going to take this middle line, and turns out it's perpendicular to both of those lines. Now in two-dimensional space, that makes sense. Okay, this line has the same length, this line has the same length. But when you're working in three-dimensional space and you have lines that are skew, so you have to imagine these lines are not actually going to intersect down here anywhere because they're on a totally different plane. They're going past one another without touching. But by the same process, what we need to find is we could find a normal to this line, infinite number of normals going every which way perpendicular to it, but they're not all necessarily going to hit this line. As a matter of fact, none of them except for one is going to be able to cross this line perpendicular as well. So there is a vector that is perpendicular to line 1 and to line 2. It's hard to see this in 3 space, but we can kind of draw it out. Okay, wherever they happen to be closest, there's a vector that's going to be perpendicular to that line and to that line at the same time. Okay, we can call this point B and this point A. And what we're looking for then is solving, finding this point and finding the length of that line. And we're using normals to each line in order to find that common perpendicular line. So in our example, we're given these two lines. We're given L1, which is x, y, z is equal to 5, -4, -2 plus s times 1, 2, 3. And equation 2 is x, y, z is equal to 2, 0, 1 plus t times 2, -1, 1. 2, -1, 1. All right, so we're given a point on each line as well. I'm going to label our lines. This is going to be L2. This is going to be L1. Okay, and we're given a point somewhere on L2. The point is 2, 0, 1. And we're given a point somewhere on L1. That's the point 5, -4, -2. And we can label our points. This is P1, and this is P2. I'm going to jot down a couple things that we know already, okay? So AB is the common perpendicular, okay? So AB is a normal to L1 and a normal to L2. What does that mean? I'll write that down first. So AB is, maybe I'll use this symbolism already, is a normal to L1 and L2. What else do we know? Well, we have formed some right angles here in three-dimensional space. We have the angle P1AB, angle P1AB, where A is the vertex. That's a 90-degree angle. And the angle also, by the same logic, P2BA. P2BA also equals 90 degrees. So now I'm going to connect these guys, P1 to P2 or P2 to P1, however you want to think about that. That's a terrible line, but you get the point. All right, this is now the vector P1, P2. Put an arrow on there. P1 to P2. Okay, this next part is a little bit tricky, but what I'm going to explain is that the projection of P1, P2 onto any vector in the same direction as AB has the same length as the vector AB. Okay, I said it, but I'm going to draw it out for you. So we're going to take some normal. Okay, any normal is going to have the same direction as AB. Okay, so I'm going to draw that right here. We're just going to call that n. It's some n. It's heading in the same direction as the vector AB. Okay, now we have our point P1, and I'm going to draw the vector P1, P2, kind of make it look similar so that our brains can make a connection here. And now if I'm taking, and I'm going to call this P1, P2, and now if I'm taking the projection of P1, P2 onto any vector in the direction of AB, what we end up with is this right here. Okay, this is the projection of P1, P2 onto N. And this length is the exact same as the length AB. Okay, so the projection of P1, P2 onto the normal of L1, L2, L1 and L2 should say, is going to have the same magnitude as the line AB and is in the same direction. Okay, so in a sense then what we can do is we've basically said this is AB. So I'm going to write that down. If N is a vector in the direction of AB, then the projection of P1, P2 onto that vector is equal to the vector AB, same magnitude and direction. Well, what we're looking for is actually the length of that line. So all we're concerned in is the magnitude of AB. All right, so that tells us also, since these are equal vectors, I should have that there, that tells us that the magnitude, maybe I should say therefore or then, the magnitude of projection of P1, P2 onto N is equal to the magnitude of AB. And since that's what we're concerned with, that's all we need to find out. So even not knowing where A and B are, we can still determine using the projection of P1, P2 onto N. This P1, P2 we know, or we're going to find out what that vector is because we know its points, we know its tail and its head. That's going to be the same as the magnitude of AB. So that defines our next step. We're going to use the position vectors P1 and P2 to find the vector P1, P2 to determine its vector. So P1, P2 is equal to, I take the vector P2, which is our point that was on line 2, 2, 0, 1. I'm going to subtract our P1, which is the point that they gave us that is on line 1. We don't know where they are, but they're on there. And we get 2 take away 5 is -3, 0 take away -4 is +4, 1 take away -2 is +1. Nope, it's +3. 1 plus 2. All right, so now this is our vector P1, P2. Okay, and so far we've been referencing the direction that AB is going in. So AB is a normal to L1, L2. The normal is a vector in the direction of AB. Okay, so I actually need to find out what direction this is going in. And one thing I do know is that it is going to be normal to both L1 and L2. It's going to be perpendicular to both L1 and L2, where there's only one possibility, one way of finding that out. I need to take the normal is going to be then this AB, the direction of AB, I should say, not AB itself, but the direction vector for AB is going to be the cross product of my direction vector from line 1 and my direction vector from line 2. So I'm going to take the cross product of those two vectors. The direction vector from line 1 is 1, 2, 3, 1, 2, 3, cross. The direction vector from line 2 is 2, -1, 1, 2, negative 1, 1. And now I'm going to take the cross product of those, and in case we forget how to do that, we'll put the little diagram off to the side again. We've got I, J, K, I, J, K. We've got the vectors for direction vector 1 is 1, 2, 3, 1, 2, 3, and then 2, negative 1, 1, 2, negative 1, 1. We've got our, for I, we've got 2 times 1, 2 times 1, minus, looks like over here my drawing isn't that great, but you should square up your drawing, minus negative 1 times 3. Then we have, for our j's, we have 2 times 3, or 3 times 2, minus 1 times 1, just 1. And for our k's, we have 1 times negative 1, 1 times negative 1, minus, heading back up to our k's, 2 times 2, 2 times 2. Close that off, simplify it, I get 2. This is negative 3, so you have 2 plus 3 is 5. This is 6 minus 1, which is 5. And this is negative 1 minus 4, which is negative 5. So this is a vector in the direction of n, which is in the direction of AB, perpendicular to both L1 and L2. And I can simplify this because I just need it. It's just a direction vector. So it's 1, 1, negative 1. Okay, heading back over to the left, we established that the magnitude of the projection of P1, P2 onto N is equal to the magnitude of AB. And we have a formula for this magnitude. This is coming, by the way, from lesson 7.3. These notes are there in order to strike your memory. But we know that the projection of P1, P2 onto the normal is equal to the magnitude, and this is a fraction, the magnitude of P1, P2 dot n, so the dot product, over the magnitude of n. Okay, so now that's why we needed all this information about n, and we got the simplest vector in the direction of AB, and now we're getting the projection of P1, P2 onto that vector using the formula from 7.3. Which also tells us then that AB is equal to that as well. So maybe over here I'll just put AB, the magnitude of AB, because that's our original goal, right? So here we go. Let's sub it in. We got the vector P1, P2 right here. Negative 3, 4, 3 dot our normal vector, which is 1, 1, negative 1. We're going to take the magnitude of that. It's going to be over the magnitude of the normal vector, 1, 1, negative 1. And I'm probably going to run out of space here, but we'll see. Taking the dot product is, draw my line, negative 3 times 1 is negative 3, plus 4 times 1, which is 4, plus 3 times negative 1, which is negative 3, over the magnitude of this vector, which I can get by taking the square root of a squared plus b squared plus c squared. So that's 1 squared plus 1 squared plus negative 1 squared. The top here is negative 6 plus 4, which is negative 2. And the bottom is going to be 1 plus 1 plus 1. That's radical 3. And sorry, oh, cheated there. I missed my magnitude lines. We're taking the magnitude of that. So even though it's negative 2, the magnitude of negative 2 magnitude of negative 2. The absolute value of negative 2 is 2. Okay, maybe I'll leave that there. Okay, that goes back in here. So our final answer is 2 over radical 3, or as a decimal, 1.15. So the perpendicular distance, looking up here, this is what we did it for. The perpendicular distance between L1 and L2 is the shortest distance between the line L1 and L2. These are skew lines in three-dimensional space. So the line segment AB represents the shortest distance between L1 and L2 in three-dimensional space. And we figured that out, that it is the projection of P1, P2, and those, remember, those were just any points along these lines given to us by our position vectors in L1 and L2. The projection of that line onto the normal to both L1 and L2, has the same length and direction as AB. So we used all that knowledge, we got the normal vector, which is just the direction of the normal vector, the direction of AB, and then we used what we know about dot product and projections in order to determine the length of that line segment AB. So the perpendicular distance between L1 and L2 is about 1.15 units. Okay, this is an approximation. This is a non-terminating decimal. There is another way to do this, okay? And the other way to do this would be to, without going into a ton of detail, but you could find the point B in terms of, it's on line 2, so it would be in terms of t. So the point B is basically if you started from 2, 0, 1, and you moved some multiple of 2, negative 1, 1, you'd eventually arrive at point B. So point B could be expressed as 2 plus 2t, comma 0 minus t, comma 1 plus t. Okay, it has those coordinates. You could do the same thing for point A. You could express point A in terms of moving from P1, 5, negative 4, 2, in this direction by a factor of s. So some multiple of this direction vector. That would give you an expression for the point A in terms of s. And then you could find the vector AB and the distance between it. You could express the vector by, same as what we did here really for P1, P2. You'd get a long string of you'd have two vectors, one that involves t's, one that involves s's, and then you'd get a combined t and s situation for x, y, and z. And then you'd work from there, solving, like we did before, solving for t and s in two of the component equations, and then checking in the third one. That's another way to do it. I'll put a video in the link in the description of this video, and actually I like that way better. This is the way the textbook did it, so I did it this way. That's it, that's all. Your practice problems can be found on page 471. You would be responsible for being able to do 1 through 15. Thanks for watching.